Hi everyone, welcome to this continued series on understanding sense of data and pre-processing steps that are typically used in data science and machine learning project. In the previous video, we talked about missing value analysis part 1, and in this video, I'm going to continue with the second part, and the second part will be focused on some new methods for handling missing value, namely interpolation. So this is the missing value treatment part 2 of the video. And in this video, we will talk about the various interpolation methods. And some of these methods may require machine learning implementations, or using machine learning, we can build those interpolation methods. So interpolation methods play a vital role in advanced techniques for handling missing values. And scikit-learn provides quite a few libraries or functions to handle various types of interpolation. Utilizing the algorithms like KNN imputer or iterative imputer or simple imputer, scikit-learn actually allows the data scientists to experiment with various interpolation techniques and build a more robust method to ensure the missing values are represented with something which is good for machine learning. I'm not going to cover all of the interpolation methods. There are 20 plus different interpolation methods. I'm going to show you some basic idea about linear imputation and also a couple of methods from scikit-learn libraries. So let's look at a basic imputation. Let's say we have some data set about cars, and in this we are recording the speed of the car at different points of time. But due to some error in measurements or collection of data or storage of data or transmission of data, we have some missing values at certain points. Let's say time interval 4 and time interval 7, we have missing values. So how we can interpolate here in this case? So linear interpolation is a method that I'm showing you here. Let's talk about this time step 4 and the value how 30 we estimated here. So first we have to identify the missing values. The missing values are at the point 4 and 7. So we're talking about 4 at this point. So locate the neighboring points. For 4, the neighboring point is 3 and 5. So we look for the neighboring points. So the number of neighboring points is configurable. You can provide the number of, or you can consider the number of neighboring points depending on your, choice. To interpolate the missing values at the point time or time interval 4, you just need to look at the known values before. So let's say time step 3 and time step 5, the values are 25 and 35. Now next we need to calculate slope. The slope is the difference between the speed 35 minus 25 divided by the time interval, which is 5 minus 3. So those are sequence numbers. So that's called slope. Slope here simply means the change in the speed per time interval. That's how it is. So we have the gradient, sort of like gradient, which is 5. Now we're going to use this gradient to estimate the interpolated value at the time step 4. And the equation is quite easy. So for time step 4, what we're going to do is we take 25, which is this one, and then we use the gradient minus the interval, time interval, 4 minus 1, and that's the estimated interpolated value for the time step 4. This is quite simple method and is called linear interpolation. There are some assumptions and some considerations that we have to keep in mind. Some of these I mentioned here. So it is applicable to any ordered data set. That means something should decide the order of the sample in a meaningful linear fashion. And it also assumes a linear relationship in the data points. It cannot be quadratic or cannot be exponential. In this method, although we have a polynomial interpolation as well, but I'm covering only the linear interpolation method where the data points must have linear relationship. Is commonly used in the time series data, and time series data is typically sequence, so it is used in those cases. Let's look at a simple Pandas demo, and I'm going to show you a very simple application of linear interpolation. So this is the simple, dummy data. Let's say we have this data frame and the time interval here and the values. So certain places you have the values missing, which is not a number. Pandas provides a very nice, interpolate function. And in this, if you notice, there are methods. Linear is the method that we are using here, but it supports the other methods as well. So in this case, since I have not mentioned any method, so by default is going to be a linear interpolation. So once you apply this, it's going to take the point above and point below and do exactly the same calculation. So it's pretty easy, but the consideration that you have to keep in mind is the values need to be ordered by some kind of a pattern, and those values must exhibit linear pattern. So that was the quick demo on linear interpolation using pandas. Let's talk about one more method, which is called SimpleImputer. Now, this is a library within scikit-learn. Let's see what is the purpose of this SimpleImputer and how do we use simple imputation. As the name says, simple imputation means simple imputation, and is meant for things as simple as mean, median, and most frequent, or a mode, or even the constant value. This is something that we have covered in the part 1 of missing value implementation as well. Now, this is part of the package here, and this can be applied to any data set. No need to have linear correlation or any kind of pattern. And the strategies for imputation include mean, median, or most frequent, and this is what you need to mention in the simple imputation function. And the choice of strategy depends on the data set. Quite easy. Let's see how SimpleImputer is used in scikit-learn. So here is the SimpleImputer, part of scikit-learn impute module. You just need to include in your import, get your data set. This time is a very famous Titanic data set. And here there are a couple of places where you have null values, especially in the age column and embarked column. So in the age column, you can include or introduce some missing values yourself also by randomly picking few rows from the data frame and just substitute nan forcefully here in this column age, and also we do the same, let's say 20% and 10% here, and that's going to be marked as null. So if you see here, the age column will have some places as nan, and similarly embarked will also have nan. So now we have two columns which we need to work on using the simple imputer. So here we need to create two imputers, one for the column numeric column and the other one is a categorical column. Just create the simple imputer. Mention the strategy here, mean or most frequent. Why most frequent? Because this is categorical variable, so we just go with the mode. And then we use a column transformer to include both of these imputers as part of the trigger called transformer. And in this transformer, mention both of these transformers. This is little advanced configuration of scikit-learn missing value treatment. Once you're done, call the pipeline, which is provided by scikit-learn again. I have included the pipeline from the scikit-learn pipeline. And that pipeline is going to process the preprocessor that we have configured in the one step before. Simply mention the name of the preprocessor and then fit and transform. So provide your data and is going to do the simple imputation based on the strategy that you have mentioned, mean and most frequent here. And after doing so, you can take a look at it. The imputed data frame, the age is imputed. All of these places where you had null, and similarly embarked is also, you know, the places where the null values were introduced by us is now carrying some value here. It's pretty easy to implement a simple imputer. So that was simple imputer from scikit-learn. And then we also saw the implementation using scikit-learn here. One more method that we will talk about is slightly rich and sophisticated and also very powerful, is called neighbor-based interpolation. And let's spend some time understanding what it actually means. Essentially, it means the value of a nearest data point. So we're going to consider the nearest data point and pick that value, put it into the place where the value is missing. This is applicable in cases where the relationship between the data points is expected to be a kind of like a cluster or a piecewise constant. I'm going to give you an example of what is piecewise constant, so you get a better idea. If you remember the part one of the video, we talked about California housing data set, and there were ample places where the concentration of households were like a region or like a block, or you can say is a piece. So that's the idea behind piecewise constant. Anyway, I'm going to show you some more examples to further clarify the concept behind piecewise regions. It is useful for data which is spatial in nature, for example, longitude, latitude, something which defines a region, right? So that is where it is useful. Now, this is completely machine learning based application. So if you're not familiar with machine learning, that's okay. Just hold on till you complete the machine learning primer course. In the primer course, I'm going to cover the nearest neighbor algorithm. And after that, when you come back to this, specific data handling technique called in nearest neighbor interpolation, it should be very easy to understand. So let's talk about what is piecewise constant nature of data. Certain characteristics here, it should be constant interval. That means the data or the function should remain constant over a particular interval or segments or location or region that we are interested in. And then when you transition from one region to another region, then the values should change. And that change can be very abrupt or very different. And then it's like a step. wise behavior, like like a ladder. Step one has certain characteristics, step two has certain characteristics, step three has certain characteristics, so on and so forth. So that means the values or data points will exhibit certain properties like discontinuity. So it will be continuous within a region, and then after that region, when you come to a next region, then it is discontinuous, means it's a different value, completely different value. So these are characteristics of piecewise constant. Let's take an example here. For example, let's talk about the Bangalore city or Bengaluru city, and these are the longitude and latitude in the city of Bengaluru. And then what we can think of is for each of the location, think about the number of software companies, maybe, you know, think like that. And let's say in this region, the number of software companies are let's say 100. In this region, it is although the circle size looks the same, but imagine when you switch from this region. So this is one region here. This could be another region. This could be another region, and you can see here the piece. So this is like a piece here. And within the piece, the number of software companies is constant. And here also the number of software companies in Bengaluru, in this part of the city, is constant. And likewise, here too is constant. And here too, the number of companies is constant, and so on and so forth. So that is the basic idea of piecewise constant nature. So that means, let's say a column has a missing value in this particular piece. So what we're going to do, we'll pick up a few neighbors from this piece, and let's say after taking, let's say 4 neighbors, and we average, and then we put the value in the missing place. This is the basic idea of neighbor-based interpolation. So let's take another example to make it clear. Consider we have a data set which represents the temperature in the city, again probably Bengaluru, throughout the day. Okay, and if the temperature remains constant during some specific hours, that would be called a piece. Another constant in the afternoon, that's another piece. And changes, and then the temperature of course changes, like morning to afternoon or evening. So the way it looks like is, so this is a piece here. In the morning you have 20 degree, and then in the evening 6 to 12 or 12 to 3 is 25 degrees. So that would be one segment or one section or one region, you can call it, right? And then similarly here is 30 degree. So what it means is, let's say a particular row, the temperature column is missing here, the missing value. So what we can take, we will take a few neighbors in this region and average those values and substitute here. This is what it means by interpolating by using the neighbors. So again, I'm going to show you how it is implemented using scikit-learn, and the method is knn imputer. That is your knn imputer is a machine learning based imputation technique. K stands for the number of neighbors, quite common. And so that means you have to configure, you have to provide that value. So that also means strong familiarity with the data set is highly required. So it's going to utilize the information from the k neighbors for each of the missing point to impute the values there. is very useful for imputing the missing values in a data set where the data set exhibits patterns of region, patterns of section or piece, or grades or gradient. It can be effective when the missing data points have dependencies in that location or in that local space. Scikit-learn provides a simple KNN imputer implementation. So this is called scikit-learn impute and KNN imputer. Let's say, again, like in the previous case, we have diabetes dataset, which is basically few columns, and the patient is whether diabetic or non-diabetic, and then we convert that to 0 and 1, check for any null value. There are no null values here originally, so we will introduce some missing value here. Okay, and then let's say we choose some random missing value, shape of the data set I'm providing as size. So this is the place. So randomly, I'm generating false and true. That means wherever it is true, I'll be masking it, and I'll mask the value uh, to null, or mask the value to nan here. So now let's say here I got this in the indexes randomly generated for each of the column. So that means, let me explain what is happening. This is for row 1, row 2, row 3, row 4, column 1, column 2, column 3, column 4, and so on and so forth. And this one is true. That means that one will become a nan. This is the intention here, to randomly introduce the null or missing value. So I'm using a masking method here, which takes the indexes, and wherever you have true is going to just, and notice here how it's going to happen is, yeah, I think I have some examples here. Let's say, the series of values, let's say 5, and the values are nan and 1, 2, 3, 4. So this is how you created a series of values. Let me show you. Yeah, so this is how. So what I'm saying is, find out where the values are greater than 0. First place, not greater than 0, so that is coming as nan. So I can mask it. I can say wherever is greater than 1, make it 10. Otherwise, no. So these two places will remain 0 and 1, and the other places are becoming 10, sorry. You can also say, if it is greater than 1, put it minus 10, then it is going to substitute those minus 10. Now notice here what we are doing is, wherever it is greater than 1, I've not provided anything, so that means Pandas will treat it like missing. And that's what happened in this case. I did not provide any value, so Pandas is taking any value as missing value and just substituting the missing value here. Anyway, so that was the basic idea, how to introduce, simulate missing value for just creating this demo. And after that, we do a train test split, which is again a machine learning technique to evaluate your data. Imputer needs the number of neighbors. You need to evaluate different values and see which value really makes sense for your data set and the model as a whole. Okay, so by default it will be number of neighbors 5, and that means for a missing value is going to find 5 neighbors in the data set and average the nearest those 5 neighbors values and impute in the missing value. So that's what is going to happen here. So I'm going to create the imputer, providing the training set. And let's say, we have random forest as a model, and then train the model. And after that, if you have a test sample, again, test sample need to be imputed because they will also have missing values. So impute it, and then you can predict based on this. This is roughly the idea of how we use imputers in real term. When we deal with machine learning, we will talk about pipelines and we will talk about how we orchestrate some of these steps, data processing steps in the training time and also at the prediction or inference time. So that was the demo on KNN Imputer. In this particular video, we talked about simple linear interpolation and then scikit-learn package called Imputer. And within that, we looked at a couple of methods. The interesting one was neighbors-based interpolation. The key points about KNN Imputer is designed for numeric data. It's not meant for categorical data. So if you have categorical values, they need to be handled separately. So direct handling of categorical values by using KNN Imputer is very, very limited. So that means we have to have a different method to take care of the missing values in the categorical columns. It's good for columns which are numerical in nature. Summarizing on overall best practices for handling missing values, you can try out different methods. In the part 1 of the video, we talked about the techniques like missing completely at random, missing at random, structured, and so on and so forth. So try out those methods. Domain knowledge is very, very important. Analyze the patterns, why the values are missing by looking at the missing value and also the non-missing value. Try out the combinations of machine learning method along with your domain knowledge as well. And avoid any arbitrary deletion. Do not delete data just based on limited experimentation. Conduct a thorough experimentation with all possible methods and then decide what to do with the missing value. Impute, no impute, or drop or remove from your data set. So that's pretty much it in terms of missing value. In the next video, we'll talk about how to deal with extreme values and noise in the data set. This is called outliers. Have a great day, guys. See you in the next video.